Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Students, let us understand a fundamental topic in Unit 1, electric charges in fields, the essential difference between conductors and insulators. We will ensure this explanation is simple, exam-safe, and memorable for life. Let's begin with a simple question from everyday observation. Why is it that when we rub a nylon or plastic comb on dry hair, it gets electrified and can attract small pieces of paper? But if we rub a metal spoon, no such electrification occurs.
Yes, I have wondered about this. Why does the charge not stay on the spoon?
Exactly. The spoon and the comb both contain atoms, electrons, protons. The difference lies entirely in how they handle the acquired charge.
Right.
Now consider a counterintuitive example from daily life.
Yeah.
Water. You might think water is just water, but pure water is a poor electrical conductor.
Really, a poor conductor. But we are always taught that electricity and water are a dangerous mix.
They are, and for a good reason. But that's because the tap water we use, it has dissolved salts.
The impurities.
Precisely. Those dissolved salts make it a decent conductor, and salt water, like the ocean, is an excellent one. This shows that the conductivity can vary drastically. We need to understand the material's internal structure to explain these phenomena. The core idea is simple. Materials are classified based on how easily electric charges, specifically electrons, can move within them.
So it's all about movement.
All about movement. Some materials, called conductors, allow charges to move freely, while others, called insulators, prevent this movement, essentially trapping the charges in place.
Yeah.
This ability to permit or prohibit charge movement determines almost everything about the material's electrical behavior. Let us understand this through an analogy. Imagine electric charges are cars.
No.
A conductor is like a multi-lane highway with no tolls. The cars, our electrons, they flow freely without obstruction.
Makes sense. A clear path.
Conversely, an insulator is like a toll booth with impossibly high fees. The cars just cannot afford to move, so they stay trapped in place. At the atomic level, think of atoms as houses. In a conductor, the outermost electrons are loosely bound, like lodgers who can freely wander from house to house. This wandering movement facilitates charge flow.
And in an insulator?
In an insulator, however, electrons are tightly bound. They are like prisoners locked in cells with high energy barriers. They cannot leave their assigned atom.
So the difference is about whether the outer electrons are loosely held or tightly held by the atom.
Precisely. The quantum mechanical energy barriers are just too high for electrons to escape in an insulator, even when an external electric field is applied. Now that we have the core idea and mental image clear, let us see how NSERT formally defines this concept, which is crucial for examination writing. I request you to read the formal definitions of conductors and insulators from the source.
Of course. Those which allow electricity to pass through them easily are called conductors. They have electric charges, electrons, that are comparatively free to move inside the material. Metals, human and animal bodies, and earth are conductors. Most of the non-metals, like glass, porcelain, plastic, nylon, would offer high resistance to the passage of electricity through them. They are called insulators.
Very good. And let us note that there's a third category, semiconductors, which offer resistance intermediate between conductors and insulators. Now, let's re-emphasize the consequence of this difference. 1. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor.
The whole surface, not inside, in the volume.
No, on the surface. We will learn why later, but for now, remember, it spreads over the surface.
How?
2. In contrast, if some charge is put on an insulator, it stays exactly at the same place where it was placed. It remains localized.
So it's stuck there.
It is stuck. And 3, the real-world implication. This is why a metal spoon loses charge immediately upon contact with your hand or the earth.
Because my hand is a conductor.
Yes. Your body and the earth are conductors, so the charge leaks through your body to the ground, whereas the charge stays fixed on a nylon comb, which is, of course, an insulator. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let us link this to current flow. In a good conductor like copper, there's an enormous density of free electrons, approximately 10 to the power of 28 electrons per cubic meter.
That's a huge number.
It's an unimaginable number. But, and this is the key, the individual drift velocity of these electrons is extremely slow.
Slow.
Very slow. We're talking in the range of millimeters per second.
Millimeters per second. That sounds like a snail's pace. How does a light turn on instantly then?
That is the most common confusion. The large current is due to the enormous density of free electrons, not their speed. Think of it like this. The signal, the electric field, travels at nearly the speed of light. It tells all the electrons to start moving at once, all along the wire.
I see. So the command is fast, but the soldiers are slow.
An excellent way to put it. The individual electron creeps, but the signal zooms. In an insulator, since the density of free electrons is essentially zero, no current flows, no matter how strong the applied electric field is. This understanding of charge movement is essential because the material's response determines everything that happens next in this unit.
Like for Coulomb's law.
Exactly. Whether charge will redistribute, affecting how we apply Coulomb's law, or stay localized. It all depends on this. Now, students, while this topic seems straightforward, there are a few common misconceptions that silent killers that can cost marks in the examination. Let us correct them now. The first common mistake is thinking that in conductors, electrons flow very fast, like water gushing through a pipe.
Right, because of the word flow. I was thinking that just now.
As we just discussed, the individual electron drift velocity is actually extremely slow. The large current is due to the enormous density of free electrons, not their speed.
Okay, so I should remember. Electrons creep, but the signal zooms.
Perfect. Do not confuse electron speed with current. The second misconception. Some students assume that insulators do not conduct because they have no electrons.
But if they can't conduct, doesn't that mean they are empty of charge carriers?
No, not at all. Insulators possess plenty of electrons. They are just tightly bound to their atoms. They block current not due to scarcity, but because the electrons are locked in place.
So insulators are electron-rich, but electron-locked.
Precisely. That is the correct concept. And finally, believing that all materials strictly fall into only two classes, conductor or insulator.
But we did mention semiconductors.
We did. The reality is a continuous spectrum. Semiconductors exist as an intermediate category with controllable conductivity. The division is not sharp. To lock this concept into your memory for the exam, let us use our memory anchors. Remember the mnemonic, CIF?
KIF.
Conductor means free electrons. Insulator means immobilized or locked electrons. And the field is what shows the difference in their response.
CIF, conductor-free, insulator immobilized. Got it.
And use this phrase. Conductors let charges roam free. Insulators lock charges tight. You can even use a physical gesture. When you think of a conductor, make a flowing motion with your hand, symbolizing free drift. When you think of an insulator, make a locked fist. It shows the charges trapped inside. To summarize our deep dive on conductors and insulators, let us note three key factual points for revision. 1. Conductors are materials containing free electrons that readily move, whereas insulators have electrons tightly bound to atoms, preventing bulk movement. 2. In conductors, any transferred charge immediately distributes entirely on the surface. In contrast, charge placed on an insulator remains localized. And 3. This conductor-insulator distinction is fundamental to designing safe and functional electrical systems, like wrapping copper wires in plastic. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam. Yes.
ProfSam.com. Thank you for joining this deep dive. Study well.